In this DeBacco University video, as the name implies, we're going to be going over radioactivity. Specifically, the three main types will be explained in a little bit more detail in this video. All right, so getting into what radioactivity is, it's the spontaneous emission of particles or electromagnetic radiation from the nucleus of an unstable atom as it transforms into a more stable form. So the whole reason why this is happening is we have an atom, for whatever reason, is unstable, but going through this process of decay, it's resulting in more stable end products. So as a result, this decay might be, for example, helium, which we represent by an alpha particle. The end result here is more stable than the initial or parent atom. In that stabilizing configuration, radioactive isotopes, which have an unstable ratio of protons to neutrons, will achieve a more stable configuration by releasing energy in the form of particles, as we'll see with alpha and beta decays, or electromagnetic waves in the form usually of gamma rays. For example, carbon-14 undergoes radioactive decay, emitting a beta particle to become nitrogen-14. And because that beta particle does contain some protons, this is why we have the change in the proton number, and that's why we have the change in the type of element. So again, main types of radioactive decay here. We're looking at alpha decay, beta decay, and gamma decay. And we're going to talk about each of these three in a little bit more detail. So let's start with the alpha decay. And that's a nucleus is basically too large to be stable. It will release an alpha particle. And that's composed of 2 protons, 2 neutrons. It is essentially equivalent to a helium-4 nucleus, as we can see here. The resulting nucleus has 2 fewer protons and 2 fewer neutrons and is therefore more stable. It has a +2 charge and a mass of about 4 atomic mass units, abbreviated AMU. Uranium-238 decays into thorium-234 by emitting an alpha particle, as just one example. There's many more examples. You can see other ones here. A quick summary is our parent molecule result in a daughter molecule and alpha particle, and these resulting end products are more stable than that original or parent molecule. If you're not familiar with the AXZ notation, remember X represents the element number, Z represents the proton number, and A is the mass there. So the alpha particle has a +2 charge to the 2 protons. Alpha decay reduces the mass number by 4 and atomic number by 2. And let's just see a quick example. Here's our uranium going to our thorium and our helium molecule or alpha particle being released here as a visual representation. Now getting on to beta decay here, there are 2 forms. Typically when we hear the term beta decay, it's referring to this beta minus decay, which is a neutron transforming into a proton, emitting an electron or beta particle and an antineutrino. For example, carbon-14 decays into nitrogen-14. Beta plus is a proton transforming into a neutron, emitting a positron and a neutrino. Not quite as common, so if you just hear the word beta decay, we're referring to this beta minus decay. The beta plus in this example will be fluorine-18 decaying into oxygen-18. So that beta minus, or just that regular beta decay, increases the atomic number by 1, and the neutron to a proton, there's no change in the mass number. In the particles or electrons, there's a -1 charge. The beta plus decay decreases the atomic number by 1. The proton goes to a neutron, no change in the mass number, and particles or positrons have a +1 charge. So again, if we kind of see our little examples down here of our neutrino and our electrons, carbon-14 going to carbon-14, carbon-10 going to boron-10, where our traditional beta decay or beta minus, the neutron is becoming a proton and we're losing that beta particle, which is in the form of electron. So we see that change in our proton number. We also see that electron being emitted here as well. In our traditional beta decay, also known as beta minus. Now, types of radiation, looking at the gamma decay, this is the emission of high energy gamma rays, which are electromagnetic radiation from an excited nucleus, often following a beta or an alpha decay. Gamma rays have no charge or mass, so cobalt-60 emits gamma rays after a beta decay as an example here as we see that occurring. Now that gamma decay does not change the mass or the atomic number. It involves only energy release. Gamma rays are neutral and have no charge. So again, if we see that here, we're seeing the acknowledgement of that energy being released, but essentially no change in the proton number, the neutron number, and therefore the resulting mass or charge of that original atom. There's other types of radiation. There's also neutron emission, which is a type of radioactive decay where an atomic nucleus releases a neutron, which is essentially a neutral particle. Remember, in contrast, alpha or beta radiation involves charged particles, so just a little comparison between those two. And there's also spontaneous fission, which is a type of radioactive decay where an unstable atomic nucleus splits into two or more smaller nuclei, often accompanied by the emission of neutrons and gamma rays without external influence. Less common in alpha or beta decay, that's why those will be our focus, but this is significant in nuclear reactors and weapons, as well as the natural decay of heavy elements. So again, just because it's not that common doesn't mean it's not important. We'll focus initially a little bit more on the more common alpha and beta decay, but when we get into nuclear chemistry, this spontaneous fission can also be taken into consideration. And lastly, the penetrating power of our alpha, beta, and gamma rays. Radiation's ability to penetrate matter varies significantly between the different types. Alpha particles have the lowest penetrating power. So if we have alpha, beta, gamma, X-rays, and neutron rays here, we've got paper, we've got thin aluminum, we've got thick lead, and we've got water or concrete. We can see just a thin layer of paper is able simply to stop the alpha particle. The beta particles can go right through the paper and are prevented from passing through the thin aluminum. And the thick lead here stops the gamma rays as well as the X-rays. And the neutron rays are the most strong. Those are only stopped by water or concrete. Another visual representation that we can see here is we've got our paper, aluminum, and our lead. Alpha stopped by the paper, probably it's just such a big molecule. Beta can pass through the paper but stopped by the aluminum. And lastly, our gamma rays pass through the paper, aluminum, but are stopped by the thick layer of lead. So hopefully that allowed you to understand a little bit more about the different types of radiation.